All right, let's go.
Number 12. The Splitting World. In 1957, a Princeton graduate student named Hugh Everett proposed a solution to one of quantum mechanics' oldest problems, and in doing so, accidentally proposed the most literal parallel universe theory in modern physics. Standard quantum mechanics says a particle exists in superposition, multiple possible states at once, until it's measured, at which point it collapses into a specific outcome. Nobody has ever adequately explained what collapse physically means or why measurement should be special at all. Everett's answer was to remove collapse from the theory entirely. Every possible outcome of every quantum event happens. The universe itself branches, splitting into separate, equally real worlds, one for every possible result. Under the many worlds interpretation, there isn't one you reading this sentence. There are countless yous in countless branches, each one experiencing a slightly different outcome of the near-infinite quantum events happening in your body and your environment every second. Physicist Bryce DeWitt popularized the theory in the 1970s and coined the name that stuck. Mathematically, many worlds is exactly equivalent to standard quantum mechanics. It makes no different predictions, which is precisely why the interpretation remains genuinely unresolved among physicists rather than settled. Here's the part that makes it the most unsettling entry on this list rather than the most promising one. If many worlds is correct, you are, in a real sense, already splitting into parallel universes constantly, every time a photon hits a detector or an electron passes through a slit. You are never traveling to a parallel universe under this theory, because you're already producing new ones faster than you could ever count them, and every version of you is permanently sealed off from every other, with no physical mechanism, even in principle, for the branches to ever reconnect or communicate. Number 11. The Bubble Next Door. In 1979, physicist Alan Guth proposed cosmic inflation, the idea that in the first fraction of a second after the Big Bang, the universe underwent an unimaginably fast exponential expansion, ballooning outward faster than light before settling into the slower expansion we observe today. Inflation solved several major puzzles about why the universe looks the way it does. It also, almost as a side effect, implied something much stranger. Physicist Andrei Linde and cosmologist Alexander Vilenkin independently developed the theory further into what's now called eternal inflation. Because the quantum field driving inflation behaves probabilistically, inflation doesn't have to stop everywhere at once. In some regions, it ends, cooling into a universe like ours, what physicists call a bubble or pocket universe. In other regions, inflation simply keeps going, forever, endlessly spawning new bubbles, each one potentially governed by different fundamental constants, different particle types, or entirely different laws of physics depending on how inflation happens to end there. Under eternal inflation, our entire observable universe is just one bubble and an endless, still expanding foam of other bubbles, each one causally disconnected from every other by the same runaway inflation that created them. That disconnection is the entire problem for anyone hoping this counts as a travel method. The space between bubbles is, by the mechanics of the theory itself, expanding faster than light can cross it. There is no direction to travel in, because the space separating one bubble universe from another is actively growing faster than anything inside either bubble could ever move. Number 10. The collision search. If bubble universes exist and occasionally sit close enough together in the eternally inflating foam, there's one scenario where they might actually interact, colliding with each other early in their existence before they expand permanently out of reach. A collision like that wouldn't let anyone travel between universes, but it would leave a physical scar, a faint ring-shaped imprint pressed into the cosmic microwave background, the relic radiation left over from the early universe that still fills the sky today. In 2011, physicist Stephen Feeney, then a PhD student at University College London, working with Matthew Johnson, Daniel Mortlock, and Hiranya Peiris, built the first algorithm specifically designed to search for these disk-shaped collision signatures in cosmic microwave background data from NASA's WMAP satellite. The team found 4 candidate regions with temperature patterns consistent with what a bubble collision might look like. They were careful and explicit that this wasn't confirmation. Humans are extremely good at finding patterns that aren't really there, and the candidates didn't hold up as statistically significant once the full uncertainty was accounted for. Follow-up analysis using the European Space Agency's more sensitive Planck satellite data didn't produce a confirmed detection either, and researchers have continued refining the search techniques through the 2020s, including newer statistical methods published as recently as 2025, aimed to squeeze more sensitivity out of next-generation CMB experiments. This remains the only genuinely observational test that's ever been run for a multiverse theory. It hasn't found anything yet. It also hasn't ruled the idea out. Number 9. The Higher Brane. String theory in its most developed modern form requires more than the 3 spatial dimensions we experience. One version of the theory, called brane cosmology, proposes that our entire universe is a 3-dimensional membrane, a brane, floating within a larger, higher-dimensional space that physicists call the bulk. Other branes could exist nearby in that higher dimensional bulk, each one a complete universe of its own, separated from ours not by distance in the ordinary sense, but by a dimension we have no sensory access to at all. Physicists Paul Steinhardt and Neil Turok developed one of the most striking versions of this idea into what's called the ekpyrotic or cyclic universe model. In their proposal, our brane and a neighboring brane periodically drift together and collide, and the collision itself, not an initial singularity, is what triggers something resembling a Big Bang, restarting the universe's expansion cycle. Under this model, the Big Bang wasn't necessarily the beginning of everything. It may have been the latest in an endless series of collisions between our universe and its higher dimensional neighbor. The bulk in every version of this theory is only accessible to gravity itself. Every other force, including light, is confined to the brane. That's not a minor engineering obstacle. It means that even if another brane universe is sitting right next to ours in the higher dimension, nothing that carries information the way we understand it, no signal, no matter, no observer, has any known physical channel to cross into it and report back. Number 8. The Spacetime Tunnel. Wormholes are the closest thing to a genuine travel mechanism on this entire list, and also one of the oldest ideas here. In 1935, Albert Einstein and Nathan Rosen described a mathematical solution to Einstein's own field equations, showing that 2 distant regions of spacetime, or even 2 entirely separate universes, could theoretically be connected by a bridge, now called an Einstein-Rosen bridge. Physicist John Wheeler later showed that this basic version would be useless for actual travel. It collapses in a time frame far shorter than it would take even light to cross it. In 1988, physicists Michael Morris and Kip Thorne worked out what it would actually take to keep a wormhole open long enough to pass through. Their answer? Exotic matter, a hypothetical substance with negative energy density, essentially a form of matter that gravity repels rather than attracts. Ordinary matter, no matter how it's arranged, cannot hold a wormhole's throat open against its own gravitational collapse. Something has to actively push back. Small amounts of genuinely negative energy have been produced in laboratory conditions through quantum effects like the Casimir effect, but nowhere near the scale, density, or stability a traversable wormhole would require. Research through 2024 and 2025 have continued exploring whether modified theories of gravity might reduce or eliminate the need for exotic matter entirely, and newer theoretical wormhole models have proposed exotic configurations, including ones that could in principle connect not just different places, but different times. None of this has closed the actual gap between the mathematics which permits wormholes and the physical universe which has never been observed to produce or sustain the negative energy density required to build and hold one open. Number 7. The Entangled Bridge. In 2013, physicists Juan Maldacena and Leonard Susskind proposed one of the strangest ideas in modern theoretical physics, condensed into a 4-character equation, ER equals EPR. Their conjecture connects two concepts that, on the surface, have nothing to do with each other. ER refers to Einstein-Rosen bridges, or wormholes. EPR refers to quantum entanglement, the phenomenon where two particles remain correlated no matter how far apart they are separated. Maldacena and Susskind's proposal is that these aren't two different things. Every pair of maximally entangled particles, they argued, is connected by a wormhole, an unimaginably microscopic one, far too small and unstable for anything to pass through, but a genuine wormhole nonetheless. In November 2022, a team led by Caltech physicist Maria Spiropoulou used Google's Sycamore quantum processor to run a simplified simulation of this idea, teleporting quantum information between qubits in a way that matched the predicted signature of information passing through a traversable wormhole and a simplified toy model of gravity. The result made international headlines, though the physicists involved were careful to describe it as a holographic simulation of wormhole dynamics on a quantum computer, not the creation of an actual wormhole in physical spacetime. Continued research through 2024 and 2025 has focused on formalizing exactly what ER equals EPR does and doesn't imply operationally. If the conjecture holds up, it doesn't hand humanity a travel method. It suggests something arguably bigger, that the geometry of spacetime itself might be woven directly out of quantum entanglement, meaning the fabric connecting potentially separate universes was never really absent. It was just built at a scale and in a form nothing macroscopic, including us, could ever hope to travel through. Number 6. The Black Hole Door. Popular science has long floated black holes as gateways to other universes, and the mathematics, in a narrow technical sense, doesn't entirely rule it out. The Einstein-Rosen bridge, originally described in 1935, is mathematically a black hole connected to a white hole, a theoretical object that only ejects matter and never absorbs it, with the bridge between them functioning exactly like a wormhole. Physicist Roy Kerr's solution for a rotating black hole even avoids the crushing central singularity that a non-rotating black hole has, replacing it with a ring-shaped structure that some interpretations of the mathematics suggest could theoretically connect to another region of spacetime entirely. The physical reality is considerably less promising. The Einstein-Rosen bridge inside a real black hole is non-traversable, exactly like the original 1935 version. It would seal shut faster than anything could cross it. And this time, there's no proposed fix involving exotic matter because the geometry inside an actual black hole isn't the clean, idealized case the mathematics assumes. Real black holes form from collapsing stars, spin, accumulate in falling matter, and radiate Hawking radiation over cosmic timescales, all factors that further destabilize any hypothetical bridge. And crossing the event horizon in the first place is by definition one-directional. Nothing that falls in has ever been observed or is predicted by general relativity to come back out anywhere at all, let alone in a different universe. Number 5. The Loop in Time. In 1949, mathematician Kurt Gödel, working alongside Einstein at Princeton, discovered a genuinely unsettling solution to Einstein's field equations, a rotating universe in which spacetime curves back on itself so severely that an object could, in principle, travel forward through time and arrive back at its own past, a closed time-like curve. Gödel's solution required a universe rotating in a way ours demonstrably isn't, so it was never taken as a description of our actual universe, but it proved something Einstein's equations don't forbid on their own. Physically consistent solutions exist in which cause can follow effect in a closed loop. Reaching a genuinely different, parallel timeline rather than looping back into your own past would require an even stranger structure layered on top of a closed time-like curve, and no confirmed physical mechanism for building one has ever been proposed. Physicist Stephen Hawking responded to this entire category of solutions in 1992 with what he called the chronology protection conjecture, the proposal that the laws of physics themselves, likely through runaway quantum feedback effects that would destroy any structure attempting to form a closed time-like curve, actively prevent these loops from ever being physically constructed, even though nothing in general relativity's pure mathematics explicitly forbids them. Hawking never proved the conjecture outright, and it remains unresolved rather than confirmed, but it captures a pattern that shows up again and again across this entire list. General relativity's equations are frequently more permissive than the universe actually appears to be, and some piece of physics not yet fully understood, seems to consistently step in and close the loophole before it becomes physically real. Number 4. The decaying vacuum. Quantum field theory describes our universe's vacuum, the seemingly empty state of lowest possible energy, as potentially not truly the lowest energy state available. Some models suggest what we experience as empty space might actually be a false vacuum, a local minimum sitting above a deeper, more stable true vacuum state elsewhere in the theoretical landscape. If that's correct, a bubble of true vacuum could, in principle, spontaneously nucleate through quantum tunneling anywhere in space, then expand outward at close to the speed of light, converting everything it touches into a new physical reality with potentially different fundamental constants. This isn't really a travel method in any sense a person could use. Nothing survives the boundary of an expanding true vacuum bubble. The transition would happen far faster than any warning could arrive or any biological process could react. What makes it relevant to this list is that some theorists treat vacuum decay as functionally equivalent to the birth of a new pocket universe, spontaneously carved directly out of the space our own universe currently occupies, a version of universe creation that requires no exotic matter, no higher dimensions, and no engineering at all. Just enough time and enough universe for quantum tunneling's astronomically small odds to eventually land in the wrong place. Current measurements of the Higgs field, one candidate for driving exactly this kind of instability, suggest our vacuum may indeed be metastable rather than perfectly stable, though calculations of the timescale involved put the expected weight at a span of time vastly longer than the current age of the universe, which is the only reason this entry belongs on a list of theories rather than a list of imminent concerns. Number 3. The simulated switch. Not every theory on this list treats other universe as a physical place reachable through space. Physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis, the argument that every mathematically self-consistent structure describes a physically real universe, meaning the full landscape of possible universes isn't something to travel to at all, but something that already exists in the same sense mathematics itself exists, independent of any physical location. A closely related idea, popularized by philosopher Nick Bostrom starting in 2003, approaches the same basic question from the opposite direction. If it's possible to simulate a universe with enough computational power, and if advanced civilizations are likely to run many such simulations, then statistically, any given observer is more likely to be inside a simulation than in the one base physical reality running it. Under this framing, a parallel universe wouldn't need a wormhole, a brane collision, or exotic matter to reach. It would only require someone, somewhere, on whatever substrate is actually running the simulation, deciding to modify the parameters, pause the process, or load an entirely different simulated reality altogether. Neither hypothesis offers anything resembling a method a person inside the universe being discussed could use to initiate travel. Both remain fundamentally untestable using any experiment physicists have proposed so far. They're included here because they represent the most radical reframing on this entire list, not a physical obstacle standing between us and another universe, but a claim that the entire concept of physical distance between universes may be the wrong framework from the start. Number 2, the observer effect. Return to the many worlds interpretation from the start of this list, and one deeply strange thought experiment sits at its edge. Under many worlds, branching happens regardless of whether anyone is watching or even alive to notice. Some theorists have explored a specific consequence of this called quantum suicide, or from the observer's own perspective, quantum immortality. If a person's continued survival depends on a genuinely random quantum event, then in every branch where they die, they simply stop having any future experience to report, while in the branches where they happen to survive, their subjective experience continues uninterrupted, and from the inside feels exactly like reality reliably favoring their survival. This is not treated as a real physical hypothesis by the overwhelming majority of the physics community, and it isn't proposed by working physicists as an actual escape route into a different universe. It's usually presented as a philosophical stress test of many worlds itself, one that highlights just how strange the interpretation's implications become once you push them to their logical edge, rather than a genuine mechanism anyone is attempting to build or test. What it captures more than any specific claim about survival is the deepest unresolved question sitting underneath the entire many worlds framework. If parallel branches are physically real but permanently causally sealed off from each other the instant they split, it's genuinely unclear whether traveling between them is even a coherent idea or a category error dressed up in physics language, since, under the theory's own rules, there is no version of you that ever experiences being anywhere except exactly one continuous branch at a time. Number 1, the unbuilt door. Look back across everything on this list, and a pattern holds without a single exception. Many worlds branches into universes that are, by the interpretation's own mathematics, permanently causally disconnected the moment they form. Eternal inflations bubbles are separated by space expanding faster than light. Brane collisions happen in a dimension nothing but gravity itself can access. Wormholes require exotic matter that has never been observed at any usable scale. ER equals EPR describes bridges too small and too unstable for anything larger than a qubit. Black holes offer one-way, non-traversable doors. Closed time-like curves appear to be actively prevented by physics not yet fully understood. Vacuum decay destroys rather than transports. Simulation and mathematical universe theories don't describe physical distance at all. Quantum immortality doesn't describe travel, only survival. Every single mechanism physicists take seriously enough to publish and debate shares the same underlying shape. The theory permits the existence of another universe and simultaneously, either through geometry, energy requirements, or a law of physics that seems to intervene right at the critical moment, forbids anything from actually crossing into it. That's not a coincidence any single paper has fully explained, and it's not obviously a coincidence at all. It may simply be what the word universe is built to mean in the first place, not a place in the way a distant country or an unexplored ocean is a place, but the entire boundary of what causation and physical law even reach. 12 theories, 0 confirmed methods. Every framework physicists actually work with insists other universes may genuinely exist, and every single one of those same frameworks, examined closely enough, quietly closes the only door it opened. Subscribe to Cosmic Hives. See you in the next one.